Okay, so should I start?
No, just a couple of minutes. Okay, good morning. Actually, this is supposed to be chaired by Venkatramana. He'll be here in 5 minutes, but it's my pleasure to welcome Professor Tsachik Gelander from Hebrew University. He'll speak on what we can learn by looking at random manifolds. Yeah, please.
Okay, so let me correct you. I'm in Northwestern. I was in the Hebrew University many years ago, but now I'm
Possible
in.
to rotate your iPad in landscape mode.
Sorry.
Maybe
I can try, but I'm much less used to do that. Okay, so let's try. So my talk is about probabilistic approach to study discrete subgroup of Lie groups. So we got used to apply randomness in mathematics in general, and we are familiar with the benefits of studying random objects. In many cases, it's much easier than to study deterministic ones, but it always feels like a miracle when we can say things about deterministic objects by viewing them as random ones, like for instance, things which has a lot of structures like SL3Z. Suddenly, when we forget that it's deterministic and think of it as a random object, we can say new things. And what I will try to convey in this talk is I will present some results. Some are older, and actually one is very new. At the end, it's a new result, and that uses this probabilistic approach. So the space that we are looking at. So we study discrete subgroups. So G is a semi-simple Lie group. And we want to study discrete subgroup of G, which is the same as studying manifold of the form G mod K mod gamma. So if you want, I want to apply randomness on gamma or on M. And so we look at the space sub G. This is the space of all closed subgroups. It has a nice topology that makes it a compact space. And inside there is an open subset, the space of a discrete subgroup. And all the results all the things that I'm going to discuss today are related to applying some to study probability measures on the space. So we want to look at probability measure on this compact space that are supported or give probability 1 to discrete subgroup, to this open subset of discrete subgroups. And yeah, so somehow I will tell you a story about consisting of several results. Each of them use a more complicated probability measure. So we start with finite measure, then we move to infinite but invariant measure. All probability measures, but and then to even non-invariant stationary, and at the end we have to consider even non-stationary measures. So I will try to dedicate about 10 minutes to each result. So let me start with the following result, which say that most hyperbolic manifolds of finite volume, most finite volume hyperbolic manifolds are non-arithmetic. So this is joint with Ariel Levitt. It was published in 2014. And and what do I mean by that? So so let's denote by rho n of v. So let's take n to be an integer, at least 4, and we consider rho n of v to be the number of n-dimensional hyperbolic complete hyperbolic manifolds of volume at most v up to commensurability. So two manifolds M1 and M2, two finite volume manifolds, are considered equivalent if there is a third manifold that cover both of them. So there is a finite cover. Or if you want, if the fundamental group of M1 up to conjugation is commensurable to the fundamental group of M2, so it means that up to you conjugate one, and then the intersection is a finite index in both. So this is the equivalence relation, and then what we found out that the theorem that we proved is that rho n of v, the number of such manifolds, behave like v to the v. So yes, and okay, and now you can show. Okay, so what does it mean? So it means that the log of rho n of v of this number is at most b v log v, and at least a v log v for two constants a and b. This is all the result. This is the result that was proved jointly with Mark Burger, Alex Lubotsky, and Shachar Moses in 2002, and this is with Ariel Levitt in 2014. But the lower bound is the result that I want to. So we use probability in a sense, and why does it say that most hyperbolic manifolds are non-arithmetic? Because the number of arithmetic ones you can show, it's actually shown in a paper by Belolopetsky, it tends to be polynomial. So it's bounded by v to the beta. It should be bounded by v to the beta, but this is not known. This is known only under the general Riemann hypothesis, but you can always show something like this. For every epsilon there is beta, such as anyhow. The number of arithmetic ones up to commensurability is very small. So this fact tell you that almost if you take a random manifold, almost surely it will be non-arithmetic. So this, if you want, it's a improvement of Gromov and Petetsky-Shapiro constructed an example in each, show that there is non-arithmetic manifold in each dimension. And here we show that most of them. And the idea was to consider a random graph. You consider a 4 regular graph, a finite 4 regular graph, and then you you take a random coloring of it, or you choose a random subset of the vertices, and then you have two pieces, two building blocks, like two manifold. Each of them is a manifold with a 4 boundary component, and let's say that one is green, and then you replace each vertex, and these are two manifolds that you can distinguish between them. Suppose that you can see the difference between them, and then you replace each vertex by one like that, and you glue them, and you get an hyperbolic manifold. You can do it compact or non-compact, and you get many hyperbolic manifolds that you can prove that they are not commensurable. So that was the idea, and you see that we use this finite probability measures, finitely supported probability measures. So in some sense, it's just counting, but it gives I think a nice result that. Okay, this of course is a simplification, so the actual proof is more complicated, and we couldn't use just 2 building blocks. We had to use 6 building blocks to do that, and yes. Anyhow, then so that's the beginning of the story. Then a much more attention was given to what is called the IRSs, that's invariant random subgroup. So these are more complicated. They're not finitely supported, but so G acts on the space of a closed subgroup by conjugation, and a probability measure mu is an IRS if it is G invariant. So if you want the space of IRS of G is the probability measure on sub G, which are invariant under conjugation, and a lot of attention was given to that space. That many people proved results. So let me give 2 examples how you can use this space to study manifolds or discrete subgroups. So the first is reproving a classical result, the theorem of Kashdan and Margulis. So now G is any semi-simple Lie group, not just SON1. It could be SLNR. And they show that there is a lower bound on the co-volume of lattices, but more precisely, they show that there is U inside G open, such that for any gamma in G lattice, for any lattice, there is a conjugate such that G gamma G inverse intersect U trivially. So that's a theorem. Now I claim that if you consider general IRSs instead of just lattices, then okay. So why first a lattice is give you an IRS. You have a map from G mod gamma to sub G, taking a coset to this conjugation, and then you can push forward the probability measure from G mod gamma to the space of discrete subgroup, and you get an IRS supported on the conjugation class of gamma. And so if you think of the generalization of Kashdan-Margulis theorem for general IRSs, you get a stronger statement, but it turned out to be much easier to prove. So the proof is straightforward. And so how you extend it? So let F be a family of IRS is weakly uniformly discrete if if there is such U, an identity neighborhood in G, such that for any mu in F, for any IRS, the probability that a subgroup intersect U trivially is at least half. So then you say that the family is weakly uniformly discrete, and then you can show by a very straightforward compactness argument that the space of all IRS, all discrete IRS of G, so all IRSs that are supported on discrete subgroup is weakly uniformly discrete. So in a sense, it is more general than Kashtan-Margulis, but much easier to prove. So really the proof is just 4 lines. So this is one result about IRSs. Let me give another result, which is more famous. So it's the theorem of sometimes called the 7 summarized paper. So this is by Miklos Abert, Nicolas Bergeron, Ian Biringer, Nick Nikolov, Jean Rambalt, and Ido Samet. So 7 authors. So the paper is long and there are many applications, but the main new result, and this was the result that motivated the study of IRSs in the non-discrete context, so in the context of continuous Lie groups. So we started to develop this theory for this result. So we show that if G is a semi-simple Lie group of rank at least 2, and let's suppose that G has also a property T. Yeah, and let Mn be if you want manifolds of where gamma n in G is irreducible lattice, and suppose that the volume of Mn goes to infinity, then we show that for any R, the volume of the thick part, where the manifold is fat, is almost everything. So when the volume of M, so in particular the thick part is non-empty. The R thick part is non-empty, and 90% or 99% or more and more, depending on the volume. And this result, we had to use, it's not like Kashdan-Margulis that you have a more complicated proof and this approach of IRS simplified. Here we really had to use this probabilistic method to prove this result. And then this result has many consequences to study analytic invariant, so like Betti numbers, normalized Betti numbers, or other limit multiplicity theorems. So it's improved many works of other people. So this is again by considering IRSs, and there are many more theorems proved in the last 12-13 years using invariant random subgroups. Now, invariant random subgroups are limited, and this is obvious because if you restrict yourself to invariant measures, then and the group you are interested is non-amenable, so you limit yourself to this very, very strong restriction. So there are many problems you cannot approach by invariant measures. And indeed, you can show that in if you want to study discrete subgroup of, let's say, SL3R, if you only use IRSs, then you cannot study thin subgroups. You can only study lattices because there is this very important theorem by Stuck and Zimmer that says that IRSs in higher rank are supported on lattices. So you cannot say anything about discrete subgroup of infinite covolume if you restrict yourself to invariant measures. So if you want to say something, you have to allow yourself to deal with non-invariant measures, and okay, and then the idea was to consider SRS. So these are stationary random subgroup. So these are much more general than IRSs, and in fact you can hope at least to say something about any discrete group by considering SRS. So what does it mean? You fix some mu, some probability measure on G. So it's a generating, if you want, it's a measure supported on a small subset that generate G. Okay, you have to choose it wisely. But then a measure nu on a G space, so for instance, on the space of a closed subgroup, is mu stationary if the convolution, if it is a fixed point, if it's harmonic with respect to mu, and now in some sense any discrete group is associated to some stationary measure, because you can start with gamma in any discrete subgroup, and then you can look at the Dirac measure on gamma, and then you can apply a random walk with respect to mu on the space of discrete subgroup. So you look at convolutions like that, convolve I times, and then you can look at the ergodic averages of this, and then you can take, so this not necessarily converge, but the space of measure is weak star compact. So there is a limit, and the limit will be mu stationary. Every limit. So if you have a way to study, if you can develop the theory of mu stationary measure, so if you can say something about stationary measure, if you can analyze them, then you may hope that that the property that you can say on the limit retains some information about the group you started with. And so here is I'm discussing my recent work, more recent work with Nikolai Frakchik. So we proved so it's also so the theorem that we proved answer a question of or a conjecture of Margulis. So let me say some definition. So a subgroup delta in G. So this is a general definition. So if you have a locally compact group G, a subgroup delta is called confined if there is a subset C which is compact, such that C intersect any conjugate of delta non-trivially. So this conjugation, if you is non-empty. So the intersection of C with any conjugate of delta is non-empty. Then it is called confined. So equivalent. So if gamma is confined, if delta is confined, this is equivalent for discrete group, for delta discrete. This is equivalent to say that the manifold M, which is G mod K mod delta, suppose that G is semi-simple, has bounded injectivity radius. So that's equivalent. And if you want delta in G, it's also equivalent to say that delta in G is not confined. If and only if you can, there is a sequence Gn in G such that Gn delta, Gn inverse, the conjugation, converge to the trivial group in the topology of closed subgroup, in the Chabuti topology. So that's equivalent to be not confined. So that's a confined subgroup, and the conjecture that we proved was that in higher rank, so the theorem is that, let's say, if G is simple of higher rank, so if there's also a version for semi-simple, but if G is simple, okay, let me actually, if G is semi-simple, and has property T, then delta in G is confined if and only if delta contain a lattice in a factor. So if G itself if G itself is simple, like SL3R, then confined subgroup are lattices. If G is not simple, like a product, if G is G1 times G2, you can be confined in G1, you can be a lattice in G1, and then you are confined. But that's the only way to be confined in higher rank. G is simple, semi-simple. Sorry, and the rank of G is at least 2. It's not true in rank 1 because the normal subgroup theorem is not true, and this is an improvement of the normal subgroup theorem. It's if you want a geometric version of the normal subgroup theorem. So example, the example is that let's say if gamma inside G is a uniform lattice, and delta is a normal subgroup of gamma, which is not trivial, then delta is confined in G. So for instance, if G is a rank 1 Lie group like SPN1, and gamma is a uniform lattice, then gamma is Gromov hyperbolic, and it has a normal subgroup of infinite index, which is non-trivial, and then you get a confined subgroup, which is not a lattice. But in higher rank, you cannot have it. And the idea to prove it was to consider stationary random subgroups. We relied on another recent paper of Aryeh Levitt, Margulis, and myself that prepared or made the analysis of a stationary random subgroup by proving a quantitative estimates about. So the idea was we wanted to get a quantitative version of the Kashdan-Margulis weakly uniform discrete theorem, and so this could be used to study general stationary random subgroup supported on discrete subgroup, and of course we had to use remarkable theorems of Neveu and Zimmer from the beginning of from 2000, and so they classified the stationary action of higher rank groups, and we used their theory and applied it to stationary action on the specific space of closed subgroup, and in particular discrete subgroups, and that was made the combination of these results made this possible. Okay, so now I have some time to discuss a very new result, which is it's not posted yet. It's a joint work with Ariel Levitt and Uri Bader. And what we did is we wanted, so one thing that we did, or the main motivation was to extend my work with Tsachik to the case that G does not have property T. So we're all familiar with the Margulis normal subgroup theorem. So that's a remarkable theorem, and it's remarkable in several levels. So both in the general idea and both in the details of the proof, and but the general idea of normal subgroup theorem was to show that. So let me just recall. So if G, let's say, if G is higher rank, semi-simple Lie group. So G is, for instance, SL3R, or G is SL2R cross SL2R, and gamma is a lattice. Then gamma is the normal subgroup theorem. So if N inside gamma is normal, then, and non-central, say, suppose non-trivial, and suppose that G is center free, then it's a finite index. So gamma mod N is finite. If you want, gamma is as simple as possible because these groups are linear, so they're residually finite, but they don't have, they're just infinite. They don't have infinite proper quotient. So, and the way that Margulis proved that, okay, so the example, we can consider SL3Z, or we can consider SL2Z square root of 2. So that's a lattice in the second example. The difference is that here we have property T, and here we don't have. So the proof, the idea of Margulis was he proved that gamma mod N is finite by proving that it has both property T and it's both amenable. So this tension between amenability and property T is what implies finiteness. These are two analytic properties that don't get along together. So the only groups that are both T and amenable are finite groups. So okay, now in most cases, the T part of the proof came for free, or it came from Kashdan theorem. Kashdan proved that higher rank simple Lie groups have property T, like SL3R has property T, so any lattice and any quotient of any lattice has property T. So Margulis had to prove just the amenability in that case. But for this case, where G does not have property T, Margulis had to work harder, and he wrote a separate paper. And one illustration about the difficulty of this is that in his book, in Margulis' book, where he proved everything up to the last details in the most generality, I think this is the only theorem that he doesn't give all the details. So the case of a higher rank group without property T, he only proved in the book. He only proves the normal subgroup theorem for co-compact lattices. In the paper, he does it for general lattices. And indeed, since so over the years, many people proved the improvement of the normal subgroup theorem, but all these improvements are just under the assumption that G has T. In the cases that G doesn't have property T, in SL2 times SL2, there was no improvement until today of the original theorem of Margulis. Okay, it was extended by Yehuda Shalom and Uri Bader. They extended the normal subgroup theorem to other groups, but for the classical group without property T, there was no improvement until recently. And what we were able to prove is okay, so we actually proved the following. So let me give example of a proof. So if so let G be a higher rank semi-simple Lie group, and gamma in G an irreducible lattice, like so for instance, SL3 is Z square root of 2. So the theorem applies to that group. If so, delta, a discrete subgroup delta inside gamma is confined if and only if gamma delta is a finite index. So of course, normal subgroup are confined. A subgroup is confined if there is in a discrete group, if there is a finite set that intersect a finite set which is not containing the identity, and it intersect every conjugate of delta. So for normal subgroup, we can just take a singleton. So this was in the case that G has property T, it follows from my theorem with Prasad, but the new thing is that we proved it for much more general okay, for any higher rank group. And let me also state something which is a theorem even more general. So this is with the Bader, Gelander, and Levitt, and let me state it in an even stronger form. So we call that a URS, uniformly recurrent subgroup, is a minimal subsystem, minimal G invariant set in sub G. So the space of closed subgroup. Now I look at it as a compact space, and the minimal sets there are called URS. So there is no measure now. A URS.
Tsachik, excuse me. Is
Yes?
a normal subgroup always confined?
Yeah. Okay. Then it's a good question. So confined where? So here in the Green theorem, I said confined inside gamma. So if delta is a non-trivial normal subgroup inside gamma, then of course it is confined. Okay, that's it's a very good question. So let me postpone this discussion about URS, and let's say so if suppose that n is non-trivial and it's normal in gamma, then n is confined in gamma. What does it mean? Take A inside n, which is not the identity. So A is contained in n in any conjugation of n, because any conjugation of n is n. So even you can take a singleton that intersect every conjugate of n. So it means that n is confined in gamma. But it's not necessarily, n is not always, not necessary, confined in G. So in higher rank it will be, that's follow from our theorem, but for example, you can take, here is an example, it's a geometric, it's actually a nice exercise. If you take gamma to be SL2, no, let gamma to be the free group, so it's torsion free, which sit as a subgroup of index 12 in SL2Z, and this is a lattice in SL2R, of course. So you take gamma to be a torsion-free subgroup of SL2Z, so it's a lattice, and then you take N to be the commutator group. So it's an infinite index subgroup. So of course it is normal in gamma, so it's confined in gamma, but you can show that N is not confined in SL2R. So it's a normal subgroup of a lattice, a normal subgroup of a uniform lattice is always confined. But for a non-uniform lattice, in rank 1, it doesn't have to be confined in G. So I hope this answers the question. But inside gamma, of course, normal is confined. Now, let me state the more general version. So recall a URS is a minimal invariant minimal invariant G invariant subset of sub G, and we say that a URS is reducible. So here I think of G as more than one factor, but it could be actually with a simple group. One of the factors could be trivial okay. So a URS is reducible if it is supported if it is if it consists of a product. Gamma 1 cross gamma 2 we contain in proper factors. So if any subgroup of the URS is a product of groups that are contained in the factor, like gamma 1 times gamma 2, G could be simple, but then if G is simple, then the only reducible URS is the trivial group, because the trivial group is the only proper factor. So for simple group, the only trivial URS is reducible. And okay. And then you can say that another definition, so delta inside G is what we call irreducibly confined if any URS which is contained in the conjugacy class, in the closure of the conjugacy class of delta is irreducible. It's not hard to show that if delta itself is an irreducible lattice, then it's irreducibly confined. And the theorem that we proved with Uri and Aryeh, the theorem that we proved in higher rank irreducibly confined is equivalent to irreducible lattice. So a subgroup is irreducibly confined if and only if it is in irreducible lattice. So that's the theorem that we prove. And okay, technically it's quite it was quite difficult for us. And what is and of course, so we also use the probabilistic approach. We also use the but the measure that we used we couldn't use not just we couldn't use IRSs, we couldn't use stationary measure. We had to use measure which are not even stationary. So okay, so yes, so that's the new result. So somehow the motivation was to prove Stokes-Zimmer theorem for this general case of SL2 times SL2. We couldn't prove Stokes-Zimmer. We have a feeling that we may get, maybe we got a bit closer, but we still can prove Stokes-Zimmer. We cannot prove what Stokes-Zimmer says. Stokes-Zimmer says it's if you want the measure theoretic counterpart of Margulis normal subgroup theorem. It says that if G is higher rank and has property T, then any irreducible PMP action is supported on either trivial group or lattices. So the stabilizer of any point in any PMP irreducible action, irreducible meaning that every factor acts ergodically, is either trivial or a lattice. The stabilizers are always either trivial or lattices, and Stokes and Zimmer proved it again using property T. So they only proved it for the case of G has property T. For SL2 times SL2, it's still an open. It's the Stokes-Zimmer conjecture. What we were able to prove is that a version of Stokes-Zimmer for action which are not just irreducible but irreducibly confined, which means that the stabilizer are not just project densely to each factor, but the stabilizer, any conjugate limit of any stabilizer is still project densely to each factor, and then we can prove Stokes-Zimmer. But along the way we had to consider measures which are not invariant and not stationary. Okay, I think that's it's exactly my time to finish. So I wanted to apologize for you and for myself for not being there. I hoped I wish I was there, but with you. But yeah. So yeah. Thank you.
Are there any questions or remarks? No? Okay, let's thank the speaker again. Thank you.
Thank you.
Thank you. Okay, see you.
Yeah. Okay, so no questions. So bye bye.